Hello, adventurers, and welcome to Floor 9, the Halving Hall. Ask the tree a name. It will not search everywhere, only left or only right. And the half it does not choose, it never thinks of again. So the stairs out of the scriptorium climbs to a smaller room, and a colder one, where the hall of lineages sprawled, one great chart fanning into hundreds of twigs. This chamber holds a single tall chart, narrow and orderly, in a way the last one never was. Every node on it has at most two lines coming down, one bearing left and one bearing right, and the names are not scattered about. They are sorted. McCown is already here, though. You do not see him pass you on the stair. He is holding a name card and looking at the chart the way a man looks at a tool he trusts. Last floor, you asked me a question, he says without turning. You asked why my lineage tree was no faster to search than the flat list I kept on the first floor. You were right to ask. It wasn't. To find a beast on that chart, I had to read every branch. The tree remembered where things belonged, but did not remember where things were. He sets the card against the chart at the root. This chart is different. This chart has a rule. One rule, and it is the whole floor. At every node on this chart, everything to the left is smaller, and everything to the right is larger. That is all. But watch what it buys me. I want a skeleton. I stand at the root. Goblin. Does skeleton come before goblin or after? After. So I go right. To the wraith. And every beast whose name falls before goblin. An entire branch of this chart I have set aside in one step, unconsidered. Now, wraith before or after? Before. So I go left. And then there is the skeleton. Two questions, and the branches I never walked, I never had to. 1,000 beasts, and I would have my answer in 10 such questions, not 1,000. I am not reading the chart, I am having it. You will build me this, and you will build the one piece I did not have to lend you on the last floor. The tree must own its nodes and clean up after itself. The destructor you read in the Hall of Lineages, you will write here. So, last week, a node had a whole bag, and there was no order. So what we had to do last week, last module, if you remember, is we had to read every potential pathway there, right? We had that kind of recursive structure. But this week, a node is going to have at most two children. It's going to have a left and a right child, and we're going to have a rule that will bind these guys together. So the left one will be smaller than the right one. And that constraint is going to be the difference between a tree we read and a tree that reads itself. This is what we call a BST, or a binary search tree. And it's a structure that has quietly been under probably half of the fast lookups you've ever used. And so here's an example, a diagram, this invariant rule, this left being smaller than the right. If we start out here at 8, which is our root, and we compare what we're looking for, which is 7 to 8, we notice, okay, is 7 less than or greater than 8? It's less than, so we go left. To 3, we then compare again. It's greater than 3, so we go right. Compare again. It's greater than 6, so we go right. So you can kind of notice that path down there. And this will usually give us a descent, right? A scan of about base 2 log of n. Okay. Now, a few things we're going to look here is one rule turns our scan into a descent. So remember, last module we had to recurse into every child. Here, we're going to utilize this halving operation to search. And this is the whole reason BSTs exist. And we're going to utilize a command where we can recall a certain name there. Now, of course, an in-order walk is going to be a free sort. If we visit the left subtree, then the node, then the right subtree. And because everything in the left holds everything smaller and the right everything larger, the values come out in an ascending order type of style without us having to explicitly sort them. So that's another really cool benefit of this structure. So the tree doesn't just store the data, but it is sorted. Okay, so continuously whenever we insert and remove. And we're going to have a process for cataloging there. And then with floor 8, we had a recursive destructor and decopy that were handed to you to read. This week, they're going to be ours to write. because a binary search tree owns its nodes exactly the way that tree did, and a structure that's new, that uses new for its nodes, needs to also implement a delete for them and a deep copy of them and not leak them. So this recursion is going to be the same that we've written before. It's just going to have a little bit higher stakes here. Okay. And then the hardest thing is going to be removing a node. Of course, adding is easy. A new value always lands in an empty slot at the bottom. But removing a node that has two children means something has to take its place without breaking the rule. And choosing that something correctly is pretty tricky. And we're going to say that for the last video in this module. But you can kind of see an example here. Of course, if we remove 3, not a problem. If we remove 8 here, 9 would have to move up. And then if right here, what we need to do is copy the in order successor, which would be the smallest to the right here, which would be 7. Copy it up and then delete it. Okay. So here we are now in our floor 9 folder here. So we just finished floor 8. The general tree, we got the taxonomy, we got the lineage. Crucially, on floor 8, though, we looked at the recursive destructor and the deep copy provided in the code. And so we're going to write that in this module. Okay. Now, a few things that's new in the starter for floor 9. We have the hero/bst header file, of course, for our binary search tree. Okay. There's going to be 6 helper bodies. They're going to be stubbed. Today, we're going to work on 2 of them. We're going to do the insertInto and the findFrom. The node, which is has data left and right, no parent pointer, the access methods, size and height, and then the public delegators are all going to be provided. We also have hero/bst test.cpp, which has which provides a self-test bst command and 7 phases there for us to check against. The bestiary is now also a BST of type monster, keyed by name alongside the bag we've already had. So we'll have some new commands as well. Catalog, recall, forget, benchmark BST. Okay. One thing to note here is that our catalog will not list the bestiary today. It uses an in order walk, and that's going to be a method implemented in the second video using the in order into. So today's visible win is going to be recall, where we can fast look up by name, plus the self-test providing us some green there. Catalog's full alphabetical list will be the second video's payoff. Okay. So let's go ahead and build and kind of show where we're at right now, and then we'll get to work on implementing today's fixes. Okay, let's say what's our name. There we go. And we could say self-test BST. Okay, I'm back. So you may have noticed there a second ago, everything was okay. I was using the solution file again. So I went and got our stubbed version here. And you'll notice now empty's okay, but you notice we get fails on the rest of our phases here. So welcome to floor 9, the halving hall. Last week, McCown's tree remembered where things belonged, but to find anything, you read every branch. This week, his tree has one rule, and that rule makes it search itself. Look at self-test BST. Phase 1 is green. An empty tree reports size 0 by accident. Same live omission as every floor. Everything else is red, and the catalog says the tree is empty. The storage is fine. What's missing is the rule. So we need to go to hero BST header, and we will rectify this. Let's go to hero BST header. Okay. Perfect. Now, what we need to do here now, and let's scroll down to our, there we have our BST class, and within that publicly we have our node struct. So you'll notice here a couple things to notice before we write anything. One, the node has a left and right but no parent pointer. Floor 8 needed a parent so lineage could walk up. A BSD search only ever walks down, so we don't carry one. 2, the public insert here. Let's see, where are we? There we go. The public insert, for example, and the same as find are already written. They just delegate to helpers we're about to write, insert into and find from, passing the root underscore. Same pattern as floor 8. Size and height, those methods are provided too. They're the exact recursions we wrote last module. So we owe 2 private helpers, and we're going to do insert first. Okay. So you notice here, right, when we insert, we just say the root's going to be, we insert into the root the value. We look for contain, we find from. Okay. Once again, find, we return find from as well. Okay. So we have a bool and then that const where we can find something as well. And then we have an in order as well where we use the in order too. So essentially we have these functions that are going to delegate as we did last week. Okay, so let's go ahead and for our insert into stub, we're going to fill this thing out here. So the first thing we're going to do is I'm going to say if n is equivalent to null pointer, I'm going to return new node of value. Okay, so that's our initial one if it's empty to start out with. I'll also say if the value is less than the data at n. Okay. Then I'll say n at left is going to be equal to insert into n at left the value. Okay. I'm going to say else if n of data is less than the value, I'll say n of right is equal to insert into n of right, insert in the value, and at the very end of the day, we'll return back n. Okay, so if n is null, that's the empty slot where the value belongs. Make a new node. Done. Otherwise, smaller, recurse left. Larger, recurse right. Equal, fall through and do nothing. A set, no duplicates. And here's the one subtlety here. We return the subtree root, and the caller writes in of left equals insert into. So we relink as we come back up. That return and relink pattern is quiet right now, but on the last video, remove leans its whole weight on it. So notice it now, insert is the same walk as find. It just keeps going until it falls off the bottom into an empty slot. Okay. So just kind of notice that we're kind of we're checking here to see if we're empty. And we check then to see, okay, well, are we less than the value, or is the value, or is that data point less than the value we're looking at? Otherwise, that needs to be, there we go. Otherwise, we'll insert into and we'll be checking in of left a value or in of right a value. I think I accidentally said insert into that value into left earlier when I was showing this. But what I'm saying is we're recursing into, right? So we're going to be checking that. So just to be very, very plain, right? We're going to be recursing until we end up hitting that slot where we can then insert in somebody. Okay, so we have that one. We then go down to our findFrom stub here, and we'll implement that one. So of course, obviously we'll start off, we'll say if n is equivalent to null pointer, we'll return null pointer. Okay, so that's kind of our guard there. I'll say if the value is less than the data at n, we'll return findFrom. So it's going to be our recurse here. Say findFrom n of left and the value. if n of data is less than the value, I'll return back findFrom n of right value, return n. Okay, perfect. So notice here as well, I did want to say one thing here. We have this case here where we're checking to see if it's empty, and if it is, we'll create a new node. Otherwise, we'll keep recursing. And then finally, at the end, we'll return back. Remember, we return back the root there, okay? So and I think I said this a minute ago, just to make sure we relink as we come back up, okay? So return and relink pattern here. Okay. Now, right here, what we see is for this findFrom, you notice here we have this if n is equivalent to null pointer. Null means we fell off the bottom here. We didn't find anything. So we return null pointer in this case. If it's smaller, we go left. If it's larger, we go right. And if it's neither, it's equal. And therefore, that's our node, so we return it. Now, you put this next to floor 8's findFrom in our head. Last week, we looped over every child and recursed into all of them. Here, there's no loop. We have one comparison that picks the direction. That is why this is log of n, and the flat list was n. Okay. Perfect. So let's go ahead and build this. Okay, let's now do our self-test on our BST. Okay, and so we can see here, I had to go for just a second there. We had an issue with some of my tests. A couple of my tests weren't actually testing the right thing, so I was getting a couple passes here later when we shouldn't have. What we should see here now is we get a few different phases okay. We'll see here, of course, phase 1 is good. Phase 2 and 3 are now okay. And then we have our degenerate as well. Phase 5 is green as well because it only needs the insert. Phases 4, 6, and 7 are still red. Those are going to be handled in video 2 and 3. And now we can use our recall command. So I could say recall lich, and you can see I can search the tree now. So you see it has 35 HP, 6 attack, its weakness is holy. Recall from the tree. I could recall the Drake. And you notice this is something that is not in Scrivener McCown's catalog, so that works. And I can also call my catalog. Okay. Okay. So I had to go back. I actually had our harness for my test here for catalog also was not fixed. A couple little bugs there when I was moving over from the bag to the BST, fitting it in with some of our older code. But hey, that's how it is being a software developer, right? So now when we do catalog, we'll notice we get 15 creatures are in the tree, but our in order came back empty. So that's what we should have gotten there. We should have said, hey, we can insert and we can see how many creatures are in the tree, but nothing yet knows how to read them out. Okay, and so that's going to be in the next video there. And of course, we could do recall lich still, recall Drake, perfect, and then catalog. Okay, and so this is where we will end this video today. And in the next video, we're going to work on the free sort, and then the debt from floor 8 comes due. Hope you enjoyed this video. It was a pleasure being with you as always, and I'll see you soon. Bye-bye.